All right, great. Welcome back. So today is the second to the last lecture. Today we will be talking about model comparison. Before we talk about model comparison, let's do our usual stuff, the Bayesian warm-up. So briefly, let's think about what we have talked about the last time. So last time it was a little bit technical. In the last week, we talked about model optimization. So we had covered 4 main approaches to optimize models. The first one is to prepare everything you can, right? To prepare everything as much as you can outside STAN. So STAN is the place to do the model estimation, and the other stuff you do it in R, in whatever, Python, in MATLAB, as much as you can. And then the second one is to come up with a proper model. One approach is to go to the literature to see what are the models that have been used previously by researchers when they are investigating similar research questions. And the third one is vectorizing. The vectorizing means as long as we write something in loops, in for loop, for example, from looping from the first one to the last one, we might want to think about that if we could avoid using loop by taking the advantage of the data type of vector, of matrix, okay? And these 3 optimization approaches, we didn't really cover too much because we mentioned that already earlier in the semester, in the lectures. We actually spent quite some time in discussing the reparameterization when we were trying to optimize our model. So here, let's say why we were trying to do the optimization. It is because when we were trying to fit the model to the data using a simple Riesler-Wagner model, we do not fit data from only one person. We fit the data from multiple participants. And to take the advantage of fixed fitting and the random fitting, we came up with the hierarchical fitting, in the sense that we assume each participant's parameter, for example, the alpha, this one, the learning rates, they follow a group level distribution, a normal distribution, with 2 extra, or we can also call that hyperparameters. One is the group level mean of the learning rates. The other one is the group level standard deviation of the learning rates. Okay, so when we were trying to implement the hierarchical model of this one, and we came up with, we encountered some of the warnings STAN provided to us, in the sense that many out of the MCMC samples, they did not really converge with the bulk, with the majority of the chains with the samples. And then this motivated us to do optimization. And last time I also talked about that, why we would like to optimize that, or in other words, which part is not yet optimized. So the idea is that we have the learning rate. The learning rate is a parameter in between 0 and 1. We were giving a normal distribution here to the learning rate. That means we take only the density of that normal distribution between 0 and 1. But normal distribution is without limit, without boundary. In theory, it can be from negative infinity to positive infinity. So this kind of artificial or arbitrary cutoff causes some of the problem. So this is the unoptimized part. So we were trying to optimize this by using reparameterization. So reparameterization, last time we spent quite some time talking about that. But in short, what that means is STAN likes simple distribution. The favorite distribution by STAN is the standard normal distribution. Standard normal means normal 0, 1. Normal distribution with a mean of 0 and with a standard deviation of 1. And we use this standard normal distribution as a target, and we reparameterize our other distributions with respect to the standard normal distribution. So here, last time we talked about this table. So when we have a parameter of interest that doesn't have a limit. So what we can do is that we, so here this blue one is the standard normal, and we multiply the standard normal with the width. We change the width in the first place. So multiply that with the standard deviation, and then add that to some mean value and change the location and change the position on the x-axis. And this is basically the simplest idea of the reparameterization with respect to the standard normal. We do not always have parameters that have a range. For example, the learning rate, right? So in this case, if we are interested in parameters in between 0 and capital N in this case, and what we do, so we basically input this part into something like a softmax. So we know softmax, we introduced softmax when we were talking about the choice rule in the learning models. However, softmax is basically just a linking function. It converts some value from negative infinity to positive infinity into the range of 0, 1, okay? So then this part, before this multiplication sign, so this part results a value that is between 0 and 1. And if we want the upper bound to be capital N rather than 1, so then we could simply multiply that with a capital N. And similarly, if we would like to have something like this, lower bound is capital M and the upper bound is capital N, and then we simply multiply the range and then plus M. And then the last example is that sometimes we want a parameter that is positive without an upper limit, and also not 0, because usually 0 parameter doesn't really make any sense, right? Otherwise we just say 0, and then this means nothing. So in this case, what we can do is we take this one, the exp, so we take the exponents. So here inside of this one, it is again the reparameterized part. And after applying this transformation or converting the linking, let's say transformation, then the entire part is above 0, and it can be as large as maximum positive infinity. Basically no upper bound. Okay, good. So this is the idea of the reparameterization, and let's see how we could implement that to our hierarchical model. So here, this one, on the left-hand side, this is the model that we translated or implemented directly from the hierarchical structure. And we would like to reparameterize or optimize this part. So that becomes something like this. So the most important part is that here we will have to use the block that is rarely used before in the previous lectures. So we will use a transformed parameters block to define how the parameters of interest are linked to standard normal distribution, okay? So you see here that, for example, especially this one, the subject level raw parameters. Raw means standard normal distribution. So in this case, if you see later, I can tell you that both this one and this one, they are standard normal, okay? So let's focus on one of them is, for now, that's enough. So here, this LR_raw, it is following a standard normal distribution, a prior. So this is a standard normal. And let's go down to see how it is used, how it is implemented for us to get the actual parameter of interest, okay? So this is standard normal, and we know that standard normal will have to be multiplied with the group level standard deviation first for the reparameterization, okay? Standard normal multiply with the standard deviation. Great, nothing really spectacular, just standard normal multiply with the standard deviation and plus the standard, and then plus the group level mean. And inside this parenthesis, this is the reparameterization with respect to the standard normal without a limit, without lower bound and upper bound. However, we want a parameter that is between 0 and 1. So what we do, we will apply this transformation. So this phi approximation is basically the softmax curve, okay? And after applying this linking function, this learning rates per participant, it is between 0 and 1. Great. So similarly, this tau underscore rho, it is a standard normal. Standard normal multiplied with the standard deviation of the group level plus the mu, the mean of the group level. And because we want some number, we want to have an upper boundary. In this case, 3 or maybe 10, doesn't matter, but there is an upper boundary. So we apply similarly this phi approximation to first transfer something inside into a 0, 1 range, and then multiply with the upper bound. In this case, the upper bound is 3, but we can also change it to 10, doesn't matter. Great. And then all the others are declaration. And we know that if we want to use something, that we have to declare the parameters first, and then we go forward. Great. And as of the model parts, the left-hand side is the part that is without the optimization, and the right-hand side is with the optimization. And the core parts, we see that from here, the for loop, the participants, and here the trial loop. This is nothing else but the simple Risk-Wagner. And what we only want to change is the prior of the distributions. So here we give the normal distribution to the mean parameters and Cauchy distributions to the standard deviation parameters. And here, this is the standard normal I mentioned. And then this, starting from here, the for loop, this will be the same as before. So this part doesn't have to be optimized. We only change how the parameters are linked, and we do not change how the exact model is implemented. Great. Any questions? Yes, there is one. Wait a minute. I guess you mean this. That's the multiplicator in the last line here, 3, this one. Always need to match the upper bounds, this one. Yes, it has to be, yes. Very good point, yes. This has to be matched, yes. Yeah. So there are 2 scenarios. If you say here, this is 5, and then this is 3, this is okay, right? Because even though you multiply with 3, it will never go beyond 3, and it is lower than 5, that is fine. However, if you say here 3, and then here you say 5, you will get into trouble, because this is larger than the upper bound, and this is not accepted. So safe is here, they match. And then you have, you're safe. Good. Other questions? So just one short comment on this one. To make sure that this has no problem, so usually if you want to do this, you can introduce one extra data variable somewhere above in the data block. You say upper tau, and then you define the upper tau to be something like 10, 5, 20, doesn't matter. And then in this particular place, instead of inserting a 3, you can then say this upper tau variable, and this one as well. What is the advantage? It means that if you want to change the upper bound, you only change the upper place in the data block. You do not have to change this 3 and this 3. Maybe somewhere else there is another 3 you also have to change, but maybe you forgot, and then you will have trouble. To avoid hard coding is always a good practice. So somewhere in the data block, define that variable and then reuse that variable. Good. Other questions? Okay, great. We cover this, we cover this. Good. in some other example, if we do not have a parameter that requires us to explicitly give the lower bound and the upper bound, for example, the slope parameter in the regression model that doesn't really have a lower bound and upper bound. So in this case, this phi approximation part is not required. It is not necessary. So we only apply this phi approximation when we want to have a constrained parameter with a lower bound and an upper bound. And then this is quite crucial for the exercise later for the programming projects. So in that particular exercise, there will be some parameters. We do not really have to give a lower bound and upper bound. And in this case, you really don't need this part. And then this is a common mistake I see before from previous semesters. And then they didn't know exactly what this does. But now I'm telling you, the phi approximation only changes the range of the parameter to convert anything into a range between 0 and 1. If you do not need the limits of the parameter, the constraint of the parameter, don't use it, okay? This is something to keep in mind. Great, those are the parameters. Yeah, perfect. So if you have no more questions now, then let's move on to the next topic. So model comparison. So why we need model comparison? It is because we do not always fit only one model to the data. We have multiple models. We have, maybe in this Risk-Lavagna case, we have the simple Risk-Lavagna, we have the Risk-Lavagna with multiple learning rates, one for the positive prediction error and another one for the negative prediction error. I showed that earlier to you. And maybe we have something else. We do not have Risk-Lavagna, we have something else. We just have another learning model that potentially could also account for the variance of the choice, variance of the data. Basically anything that's theoretically possible that you are interested in and you want to test. And basically each model is a hypothesis. It is an engine that you want to test and how they could be used to predict and to first explain and then second to predict the choice of the participants. You're interested in which one's first and which one is best, which one is not really optimal. And in this particular case, we need to compare them, right? We have to do comparison to determine which one is the best one, which one is not the best one, and maybe we work only with the best one and we forget about these suboptimal models. We're not interested in the poorly performed model. So that is the motivation. We need to determine the best one if we have multiple models in the model space. Good. And what model comparison does, and it doesn't only look at how the model fits the data. So here, one quite important thing is that we have to know a concept called overfitting. So here, let's go back later. I'll show you this one. So here, let's say we have some data. All the data, they are the red dots. And we are trying to fit the model using polynomial regression, polynomial lines. And then this one, 0 order is a flat line. And then this one, first order, this is like the regular simple linear regression. And then second order, the quadratic shape. And then the third order, fourth and fifth, sixth, seventh. Good. And there are a few observations. So one is that as long as we increase the order of the polynomial, we see that the deviance between the dots and the line, they reduce a lot. So you see here, this red line and then this red line and here, this red dot and then the line here, the difference. There is some difference. And then this one, there's some other difference, which is also larger. So if you sum those differences up and take the square, for example, this will be the largest. And then if you look at here, another extreme, basically all those dots are exactly located on the line. And then this one as well. And then if you take the square rooted deviance, this will be 0, this will also be 0. This one also quite small, not really 0, but very small, okay, this one. So the observation is that as long as we make the model more complicated, so here, if we change the order, that also means the model gets more and more complex. So if we have the model and the model is getting more and more complex, the goodness of fit is measured by the square root error, let's say. So if we change the complexity of the model, the square root error, the deviance will be reduced a lot. So here, a lot of the variance is not really fitting very well, and then here the goodness of fit is very good. Okay. And then the question now we can ask ourselves is, do we want this one? Do we want this one? Or maybe we want something like this. And why you are making this decision? And what's your heuristic, if you have a heuristic? But if you do not have a heuristic, what's other criteria that you are using so that you draw this conclusion? For example, maybe this one. So the idea is that we do not collect data from the entire planet. And we collect data from a sample, or we collect some sample from a population, and we want to draw inference. That also basically means we want to predict new observations. So suppose that there is a new observation. The new observation is somewhere here, right? Somewhere here, and then on this graph here, here, and then on this graph maybe here in this blank space. Great. And then this is a new observation. And the new observation, can it also be predicted by this model, the best goodness of fit model? Can it be predicted by this model? Can it be predicted by this model? And if we have another data point, maybe somewhere here, right? Somewhere here, here, and then here. And then in this model, the deviance from here, this point and the line, it is huge. So to keep it short, the idea is that if the model learns too much from the data, then it cannot make proper predictions. So now we can go back to the previous slides, okay? So I show you this graph. Sorry, excuse me. So on the x-axis, this is the model complexity, and then the other one, the y-axis, this is the model fit. And then there are two plots, two curves. So one is the goodness of fit. So from the plots I showed you earlier, so as long as we increase the model complexity, we will always see an increased goodness of fit. However, if we are interested in the generalizability to see how the model could predict other new observations, we see that at the beginning, if we increase the model complexity, and this generalizability is also increasing. But maybe at some point, there will be a drop because the model learns too much from the data. And then in this case, this is called overfitting. And what does that mean? So basically, you can imagine what are in the data. You could imagine that the data contains two important elements. So one is the signal that we are interested in, and the other one is the noise, something that's random. There is not really a systematic pattern that maybe we can just ignore that, not really important, okay? Noise and signal. And we want the model to fit the signal, but not the noise. And overfitting, in short, basically means the noise is also fitted by the model, and the model learns too much from the data, not only the signal, but also the noise. And then conversely, there is another concept called underfitting, and usually we do not have this problem. So underfitting means the model doesn't really learn anything from the data, even not the signal. For example, in this case, the signal might look like this, presumably. However, the model doesn't really learn anything from that signal part. So this is underfitting. And so what is the goal of model comparison after we know the concept of overfitting and underfitting and the generalizability? So we are not really interested in the model that will provide the best fit. Best fit is here. You can always make it as complex as you can, and then this will be the best fit, okay, here. We don't want that because this one will give us a poor generalizability. So what we want, so the purpose of model comparison is to find which model represents the best balance between the fit and complexity. So basically here, so this might be a balance because here the complexity is okay and the goodness of fit is also okay, and then the generalizability, it is okay. So we want to balance these two parts. And the fit, the absolute fit, and here in terms of the generalizability. And then there are some other cases. For example, we have two models, assuming that the two models are equally simple. No, wait, sorry. So they're assuming that the two models could provide the balance equally, but one of the model is simpler, and then in this case, we will prefer the simpler model. So this is a little bit extreme, but it happens not really too rarely. Conceptually, that's the model comparison. Any questions? Okay, good. So far, so good. And how to apply a model comparison? How to do it? The idea is to do cross-validation. And this is, I will tell you first the cross-validation, but usually we do not use that. We use something else. But I show you how cross-validation works, and then I will introduce you some other approximations to this cross-validation. So cross-validation, I guess most of you have already heard about that from other seminars, from the machine learning seminar, for instance. So recall the idea is that we want the model to be relatively good in terms of the goodness of fit, and we also want the model to make good predictions when there are new data. And usually if we recruit participants, and if we say, well, we recruited 100 participants, and there will be no new data, right? So then we can ask ourselves, well, if there is a model that we are trying to balance the goodness of fit and also the generalizability, we want the model to perform well on new data set. But there is no new data set. There is only these 100 people, and there is no time, there is no money to recruit 20 more participants in this case, and how you could evaluate the model on some unseen data. So this is the motivation, right? And what you can do is basically, well, because you have 100 participants, you can divide the 100 participants into 5 chunks or 5 blocks in this case. And you could first feed the model to the data using only 80 participants, and then use the parameters to make the predictions onto the remaining 20 participants. Okay, so this is the idea. So here you see this in white, those are the training data from 80 participants, and then you use that result to predict the remaining 20. And you do this not only once, you do this multiple times. So if here you shift the validation part from the first block to the second block. And then the idea is the same. You use these 4, 1, 2, 3, 4 data and to predict the remaining one. And then you use these 4 to predict this one in the middle. And here in this last case, you use those data to predict this. And then overall, those 5 times of cross-validated results will be the criteria of your model performance. Model performance here, what I mean is already the balance between goodness of fit and together with model generalizability, because there is always the unseen data part. The generalizability or predictability is already evaluated by using cross-validation. Good. And what I said is that, well, we could divide the 100 participants into these 5 blocks, and we could also divide the 100 participants into 10 blocks, and each block we have 10 participants. And in this case, we will do this cross-validation 10 times because we will have more data blocks, right? The chunks to be cross-validated. As you could imagine, this one will take quite some time because first of all, you will have to divide data, and second of all, you will have to do this multiple times. In this case, 5 times, and in another case I described, we will have to do 10 times. And also remember that this is only one model, and we will do the cross-validation for one model, let's say 10 times. And we will have to do another cross-validation 10 times for second model. And if we have maybe 10 models, and we will do this cross-validation 10 times for 10 models, that means we have to do this kind of thing 100 times. And this is a lot, right? And we do not really have the time to do that, and this is a little bit tricky. So in practice, what do people do? Well, people come up with some other criteria to approximate the result of the cross-validation. And now let's talk about the other approximations of cross-validation. So here, I think from the other statistical seminars, from whatever places, reading paper, and you might heard about all those kind of information criteria. This AIC and BIC and here lower, and this one the DIC, this one the WAIC. So in short, all of them are approximation to cross-validation. Some of them the approximation is okay, some of them the approximation is not really okay. And here, because we are using Bayesian statistics, we will focus on this one, because this one, I will show you some results. This one is the best approximation to cross-validation. This one here, this means leave one out, because in the cross-validation, we have to leave something out. We use the majority part for training, and we test that on the left out part. And then this measures the out-of-sample predictive accuracy. So that this means generalizability, because there is the out-of-sample unseen data, and we want to make prediction, good prediction for this unseen data. This is the out-of-sample part. Yeah, good. So now we will move from the conceptual part to this a little bit more practical part. So the motivation is we have multiple models, we have to do comparison. And conceptually, the best way is to always do cross-validation, but this takes time and effort. And what we do is we take approximations. And I showed you earlier a few, but I don't really have to cover all of them because we will only use this one, this WAIC for model comparison. And now I'm showing you how to do that in Stan, in the language that we have been using. So if you have some knowledge about AIC and BIC, and you know that you always have to calculate the likelihood, so the log likelihood, and then there is the penalizing part. And then the same logic also applies here. So for this WAIC, there's also a goodness of fit term, and then it is penalized by some calculation that quantifies the model complexity. If the model is too complex, and then this will be penalized more, and then if the model is not really too complex, and then this will be penalized less, right? Good. And then the equation is here, and it's too much, not really interesting, and I will show you how to do that later. But now this is important. So this is from the book, and this table compares different information criteria relative to the leave one out cross-validation. So what you see here in the bottom, this is the leave one out cross-validation results, and then the other 4 rows here, they are different approximations to leave one out cross-validation. And here, this is the number that we will be focusing on. So basically, those are the results. So this is the results of leave one out cross-validation, and then this is the results of WAIC. And then here, those are the results from the other information criteria. And you see here, even though this difference, we can't really say it's huge, but this is different from leave out cross-validation. And the WAIC, it is a very good approximation, as I said, to leave out cross-validation. And you might wonder, why is that? Why this one approximates good? So one reason it is because so we use Bayesian statistics, right? And we have the posterior of the parameters. Let's say in the simple example, we have the coin flipping example. We have the theta parameter, and then we get the entire distribution, the posterior distribution of the theta parameter. And when calculating the WAIC, we use every sample on that posterior distribution. And then this is a full and complete information of what we have known about the parameter. We know where the density is high, and we also know the variance or the uncertainty of the parameter. So all those samples, they are used to calculate the WAIC information criteria. And how this is calculated, usually this is not really used in the area of Bayesian statistics, but we can still calculate that anyway. So we have to shape the posterior distribution, and let's say here this is the distribution. Let's say here somewhere there's a top, there's a peak, there's the maximum, right? And only this peak, the point part, the point estimation, yeah, that's the point estimation. So only the point estimation is implemented into this calculation. And here as well, so only the point estimation is used for this calculation. And you see here the difference. This one uses the entire information from the posterior, and you see that must be more precise relative to those criteria that only use the point estimation from the posterior, which loses a lot of information from the posterior. Good. And to implement that in Stan, and here we will be focusing on another block. So this we didn't really use that too often from earlier seminars. And the block here, this one is the generated quantity. So before we talk about the generated quantity, let me just briefly walk you through what we have seen in the Stan program. So we have the data block. We define what are the data, what we have known about the observation of participants or whatever observation, something we know, right? The data part. And if we would like to do some pre-processing of the data, we will use the block called transform the data. And then this one I didn't really use too often, but it's there. The next block is parameters, where we define everything that we're interested in. Unknown parameters. For example, the learning rate, for example, the temperature, for example, the theta parameter in the coin flipping example, and for example, the slope in the regression models. So we define everything unknown in the parameters block. And then the next block is transform the parameters block. And then this one we didn't use too often before, but we use that now relatively often in the sense that we will use the transformed parameters block to reparameterize our parameters. So in the parameters block, we define the standard normal. And then later in the transformed parameters block, we define the parameters of interest relative with respect to the standard normal. Because standard normal is really not something we want. We want the other parameters, maybe in another scale, and we want that to be transformed into the range that we're interested in. So after the optimization. Good. And then the next block is the model block, where we define the likelihood, and I don't have to talk about that too much because we know that's pretty well. We give the likelihood, and then we see how the data, the known part is connected with unknown part, the parameters, with some other calculations. And then the last block is here, this one, the generated quantities block. The generated quantities block is the place where you would like to post-process your samples. Because every sampling is done already before including the model block. So the first 5 blocks, if you have all of the 5 blocks, the first 5 blocks, they are used for this implementation and for the MC sampling. And then this is the part that will take some time, right, for the sampling from 1,000, from the first one to the 4,000th, the last one, the samples. And after the sampling, then that means we will have all of the 4,000 samples. And if we are interested in some calculation using the entire 4,000 posterior samples, what we can do and how we can do, and in this particular case, we will use this block, the generated quantities block, to post-process some calculations using the entire posterior 4,000 samples. Doesn't have to be 4,000, but let's say 4,000 because that's the default. So using the entire posterior samples. So in this particular case, we will have to declare first, because every time we use, we have to declare. We declare a variable called log likelihood, because the log likelihood will be the core calculation for any information criteria. So we say, well, this is a real number, continuous, okay, and then the size, the dimension is the number of participants. If we have 10 people, then there will be 10 numbers, right? And then we go down later. So here, the simple idea is that we repeat what we have done in the model block. So we repeat what we have done in the model block. Even though that appears to be nearly similar, nearly identical, but the purpose is different. So here, this part, when it appears in the model block, that's the likelihood. But when it appears here in the generated quantity block, it is used for some calculation, for calculating the likelihoods, to be more precise. And as said, they are nearly identical. So what is the difference? The difference is that in the model block, we will have to write a sampling statement. So we say, well, the choice is distributed as a categorical logic distribution. And in this particular case, we do not have to do the sampling statement because the sampling is done, right? And this is already afterwards. We want to know some calculation after the sampling. So what we do is that we say, well, here the likelihood is calculated by this corresponding function. So we know that categorical logic is the sampling statement, and we know that our data is discrete. And when the data is discrete, what is the term for the distribution? So when the data is discrete, the term for the distribution, it is not density, it is mass, right? We use probability mass function to describe the probability of discrete events. Okay, so this is something we talked about really earlier. So when we know that part, so we know, and also when we know the name of the sampling statement, categorical logic, and then we know that this part is for the log likelihood calculation. So you see here the LPMF, what that means? That means the log probability mass function. The log probability mass function. So this one basically calculates the log likelihood of anything inside. So here I need to go a little bit slower. So then we have to recall how the likelihood is specified in terms of the equations or in terms of the quantification. So the likelihood is P of data given theta, right? So you recall from the Bayesian equation, the likelihood is P of data given theta. P of data given theta. Good. This is given, and this is data, the choice, and those are theta. Theta is a generic term, and then this is, in the particular case of Hierarchical, this is the theta calculated from the value update. It doesn't matter, so this is the theta part, this is unknown part. So this basically means something of data given theta. And then the something is this function. And then this is already the probability mass function. So regardless of the L here, the probability mass function of data given theta. So what is that? It's the likelihood, right? So this is the likelihood. So this is why we use a form like this to calculate the likelihood. And because we want to have the log likelihood, and then they basically, well, there's the L, okay, log probability mass function. Good. Step by step, we want the log probability or log likelihood mass function from which distribution? Then this will be the same as what we used earlier in the model block. So we want the log probability mass function of data given the theta following a categorical logit distribution. Now this everything is clear, right? Because even though here this is long, this doesn't really make too much sense if you look at it for the first time. But after this explanation, I think you know what that means. Good. And then this one, log likelihood, is basically to record this one 12 by 12 and then sum it up per person. So then in the end, we will have one log likelihood number per participant. And actually, this is not a number because we have the posterior distribution. The log likelihood per person, we will also get a distribution because we are doing Bayesian, right? Good, good. So practically, what we do is that suppose we have everything completed in the previous blocks, all those data parameter model block, they are completed. What we only have to do is to complete the generated quantity block with minor change only here and here. All the others are the same as the model block. So this is in practice what we do. And so when we have this variable and when we record the likelihood variable already, how do we use them for calculating the WAIC? We will have to use a package. So the package is actually developed by nearly the same people of the standard development team. This package is called LOO, the leave one out package. So the leave one out package simply takes the likelihood variable I showed you on the previous slide, and then it calculates the WAIC for you. So this is the reason why I didn't really explain the entire calculation equation of WAIC, because this is really not important. It's better that you know it, but if you do not know, it doesn't matter because there's a package you can use. Good. Here we load the package in the first place, and then suppose this one is the feed results that you run on your local computer. We use this function to extract the log likelihood from this fitted object. And presumably, this fitted object will have a variable called log likelihood. This line extracts the log likelihood from this fitted object, and we give a name. And when we have the fitted when we have the log likelihood, then everything becomes a lot easier because we simply input the log likelihood into the function of leave one out in the first place. There are two approaches. You can input this log likelihood matrix to the LOO function. We can also input the LOO. We can also input the log likelihood matrix into the WAIC function. So both of them are okay. So, but now for the educational purpose, we focus on the second one. Okay, but both of them, they are used for model comparison, and usually they give pretty much similar results. Yeah, this one is not too important. But if you are interested, in there is a paper discussing the difference between the LOO and the WAIC. Good. Okay, good. This is the important part. So when we calculate the LOO or the WAIC, let's say LOO because this one is the result of the LOO. Similar to all those other R functions, if you call a calculation, the R function will first returns you what you have done, what has been done. So here it says the function is calculating some likelihood matrix from this dimension. 4,000 is the number of samples. 20 in this case means the number of participants. Okay. So imagine this will be a log likelihood matrix, 4,000 rows and 20 columns. And then there's a little table. There are 3 rows here, here, and here. What that means, so here this ELPD means expected log probability density of the loop. And then this is the P of the loop. P of the loop, you can imagine that kind of like the number of parameters. And then this one, this LOOIC. The IC part, then that's what we're interested in because we want to use information criteria. And this IC basically means information criteria. Great. So if we are reporting anything, so what we do, we focus on the last line. We focus on the last line. And this is the number that we will report, let's say 58.9. And you might just wonder, what does this number mean? What is 60? And how to determine which is good, which is bad, right? So let's say we have 2 models. And for one model, and we run this model WAIC calculation, and we say, this is the result, 60. And if we have another model, and then the result is 80. So now you can compare which one is higher, which one is lower. And this is easy, right? 80 and 60, which is higher? 80 is higher, and 60 is lower. And then you have to know how to make decisions. So in this case, if you know from the other statistical seminars, whatever, the AIC and BIC, if you know the rule of that, here it is the same. So it's always that the lower number indicates a better model. So what I said is 60 and 80, and in this particular case, the model that has a WAIC results of 60 will be preferred over the model with a 80 WAIC information criteria. Good. So the lower the better. That's the easy rule. That's the take-home message of today. You calculate the model comparison information criteria, and then there are multiple numbers, and you take the lower one, lowest one, and then you have the best model.
Yes, I would have a question.
Yeah.
I think, for example, the BIC can become negative as well, right?
I don't know. Why?
Is when interpreting, the more negative also the better? Or do we interpret the absolute value?
Yeah. Okay. I think I've seen negative BIC. I think I've also seen negative AIC, but the logic is the same. Yes, more negative is lower, right? Then that's better. Yes, you don't take the absolute, you take the sign into consideration.
Okay, great. Thank you.
Yeah, sure. So lower the better, always. The sign is taken into consideration. Good. Are there any other questions before we go a little bit more practice? But I show you how to do the practice. You don't have to worry. Anything? Okay, so moving from this a little bit more abstract, like monologue from me, let's look at something a little bit more interesting. We can use a experimental task. So here we will have a reversal learning task. What it appears, it is the same as what we have seen before. So we have one screen for the stimuli presentation, 2 options, one blue and one yellow, and here the participants make a choice. Blue in this case, and then get a results, 20 cents. What is the reversals? How does the reversal happen? So previously, let's say the blue option is always the good one with 80% reward probability. And then this one, 20. And from the beginning to the end, the participants, after learning, after trial and error, the participants will figure out this one will result in reward, positive reward more often relative to the other. This is a good one, basically, okay? And reversal learning simply means the reward probability is not fixed. It is not always 80% from the beginning to the end. It changes. And in this case, let's say, instead of 20 and 80 here, this is my example of 70 and 30, but doesn't matter. So the reward probability of the yellow option, it started with 70%. And after a few trials, the reward probability changes from 70 to 30, and then later 70 again, and then later 30 again. And then this reversal happens multiple times. And then the reward probability of the blue option is 1 minus. So you could imagine it starts from here and then up 70, 30, 70, okay, a few times. Good. Another observation you can see from the plot is that this length or the size is not always the same. So that means how frequent and after how many trials the reversal happens is not fixed. It is also not known, right? And this will also reintroduce some other uncertainty to the participants. So maybe after 10 trials, the reward probability changes. Maybe the next time when it happens, it has to wait until the 12th trial after reversal. So maybe it changes. So here what I can tell you is that this is a random number generating process. The length of the duration of the reversal is between 8 to 12 trials. Sometimes after 8, sometimes 9, 10, 11, 12 trials, and then this changes. And this is a good experimental design property in the sense that participants cannot predict or cannot expect the reversal. And they also have to learn, they always have to learn so that they figure out which is the better option, which is the worst option, okay? So this curve, we know that as experimenter, but participants, they don't know. They only see this screen. They see 2 options, they make twice, they see the feedback, and then they infer what might be going on. And if there is a reversal, when the reversal might be happening. So this is their task. Good. Because the experiments appears to be the same as before, and what we know about the data, we know the choices AB and AB, left, right, and we know the reward, win-loss and win-loss. The data is the same, and that basically means we can really use the previous risk-Wagner model to fit the data, because the data is the same, and only there is a reversal structure, but the model doesn't really care this, and we can apply the same model to the data. Okay, so model 1, risk-Wagner. Perfect. And model 2, if you're interested, maybe we can have the learning rates for positive versus negative outcome or prediction error. And here we will focus on another model. And this is called a fictitious reinforcement learning, or sometimes it is often, I think it is more oftenly called counterfactual risk-Wagner or counterfactual reinforcement learning. So what that means, here in this code block, pseudo code block equations, this first line, and then here, this first line, it is really showing the risk-Wagner, nothing else. Prediction error calculation, actual reward minus expectation, and then the expectation is updated by a learning rate weighted prediction error. There's nothing else, risk-Wagner, perfect. And what is this line and then this line? So we start from here. What is a minus reward? And what is that? So minus reward, you can say, well, reward we know is 1 minus 1, and then minus reward is basically the opposite. 1 becomes minus 1, and minus 1 becomes 1. That simply means the negative, or sorry, the positive, the opposite, sorry, what's the word? The opposite reward. If we choose blue, we get a win. And we know that if we were to as if we have chosen the yellow, the opposite, what we have got, Okay, with what we might have gotten if we were to choose the opposite option. Okay, so this means if we know that blue will give us a positive outcome, then yellow will give us a negative outcome. So you see here, there's the anti-correlation part. If we know one gives us a reward, the other one must give us a punishment. So there's the opposition, right? Then great, this minus R basically means the opposite reward. And then why it is called counterfactual, and it comes from here, because this opposite outcome is never really delivered to you. Because if you choose blue and you get a win, and the negative outcome or the opposite outcome, it is the counterfactual or imaginary outcome. You didn't really choose, but if you would have chosen that, what you would have gotten. So then that is the opposite. Great. And then this prediction error is basically the counterfactual prediction error. You didn't really get it, but you could infer that from the structure of the task. The prediction error NC here means non-chosen because you didn't choose it, but you can also say, well, this is the prediction error of the counterfactual part. Counterfactual prediction error equals the counterfactual reward minus the counterfactual expectation. Logic is the same. The only difference is that this is actual, this is counterfactual. And then the counterfactual prediction error is then the calculation same, multiplied with the learning rate and then update counterfactual value. Great. Any questions here? It's actually very simple. I think I made it too complicated. Only minus sign here and nothing else. All the others are the same. Good, good. So in this counterfactual Risk-Wagner or reinforcement learning model, we will update the value signals for both options. So the difference between this one and the simple Risk-Wagner is that simple Risk-Wagner, we update value only for the chosen option, only for the actual, right? Only for the actual. And in this one, we update both. We update both options. We update both the factual and also the counterfactual. Good. Yeah, this one goes to the calculation of the V of the expectation. This one I'll show you later. Then now we go to the implementation. This one I will walk you through that a little bit because last week we talked about optimization, and this week we talked about using the generated quantity block to calculate likelihoods. And all of them they belong to different blocks, and we never really see an entire full STEM model for this kind of tasks, optimized with the likelihood calculation. So now I'm showing you how that looks like from the beginning to the end, okay, like we did before. Any questions? I'm getting the file, so just feel free to ask questions if you have. Can you see my R studio? Yeah, great. So this is a model file it is complete with the optimization and also with the calculation of the likelihood. So here the data block, I don't have to explain, and we know that the data variable, number of trials, number of participants, the choices, and the reward. Good. And then this one is for reuse. I said we do not want to hard code everything, and we create a variable and we reuse the variable later. And this is the initial value, by the way, 2 zeros basically. We repeat 0 twice, 2 zeros. This one, parameters. This one, transformed parameters. Importantly, look at the link here. This is standard normal, wait, this is standard normal. Look at the highlight here. I'm not sure if you can see that clearly on your screen, but it is highlighted with a small frame. Standard normal multiplied with group level standard deviation plus group level mean. Inside, without a range, however, we want the parameter to be between 0 and 1. So this phi approximation does the transformation for the tau and multiply with 3, and we know that already. Then the model block, here I said this one is standard normal because you do have to give it as a standard normal. So nowadays, and nowadays means from 2 years ago, I think the Stan team, they, not really sure, but I think they have really another function, just standard normal. And they say this one is slightly better than this, but doesn't really change the results, only the performance a little bit in terms of the efficiency, okay? But look at the manual, as always. So here are the parameters, the priors of the parameters. These two, the group level mean before the phi approximation, standard normal as well. These two standard deviation of the group level, the Cauchy, this one, standard normal. As I said, this part I can skip because this is the model, the Riskla-Wagner. The difference, well, this is actually not the standard Riskla-Wagner because this one is the counterfactual updates. But this is really the same as I explained to you. So the prediction error non-chosen equals to the minus of the reward, the opposite of the reward, minus the unchosen option, okay? And then this is the chosen value update using the factual prediction error. And then this is the counterfactual value update using the counterfactual prediction error. The little thing that I need to explain a little bit is this 3 minus choice. This is simply a numeric trick in the sense that, look at below. If we say choice is 1, and then 3 minus choice is 2, that basically means the other choice, the opposite. So if choice is 2, 3 minus choice is 1. So this is the opposite of the choice. So 3 minus the choice simply means the unchosen one, the counterfactual choice. This is a small numeric trick. Good. Here, this is the generated quantity block. What these lines do, so these lines, they are trying to convert the group level mean of the parameters from the raw space to the actual space. Raw space means without a boundary, without a constraint, and actual space means that is the range that we're interested in. So the learning rate 0, 1 and the tau is 0, 3. We again will apply the phi approximation to make sure that the range is really corresponding to the lower and upper boundary. This one, the log likelihood variable declaration, real number, name is like this. You can also name it differently, but doesn't matter. This one, the size, right? And here, this part, as I said, nearly identical to the model block. Only difference is this line, okay? I show you the difference. So I can, don't redo it yourself, but I'm doing that for educational purpose. I copy it and paste. So in the model block, we write something like this. So choice is following or is distributed as categorical logit distribution with a softmax temperature multiplied the value vector. This is what we have known, right? So actually, if you do this way, and then there will be an error message saying that sampling statement is not allowed in the generated quantity. So what I do usually is that I create a generated quantity block blank, and then I copy the entire model part from the model block to the generated quantity block, replacing these sampling statements with the log likelihood calculation. Okay, so here there is a link, there's a connection. So log likelihood, categorical logit, that's the sampling statements. When calculating the likelihood, as I said, just add this suffix log probability mass function. And you might wonder, how do I know this? I don't, so go to the menu. You find somewhere corresponding to this section, and lower you will see what is the corresponding log probability function. It can be probability mass function. It can also be a probability density function, depends on what distribution you use, right? So here. So what I do practically is, well, if you use RStudio, you can also see, well, there are suggestions. So what I do is I change the suffix, and I also follow the rule of constructing a likelihood. Likelihood is P. Likelihood is this, right? P of data given theta. And this is the likelihood, well, sorry. This is the likelihood part. And that means the first argument or first statement has to be the data. So usually what I do is, okay, I move the choice, the data part here, and I add a little bar. Okay, good. And this is the log likelihood calculation for that particular trial. And we want that log likelihood to be accumulated for participants. And for this purpose, we use this one, okay? So this one here is the same as here. So then I just showed you how I usually do it. Good. Prediction error and the counterfactual prediction error calculation, and here the actual value update and counterfactual value updates. And whenever you do it, just also click on the check button to make sure that everything is syntactically correct. So here is model 1. What I showed you is model 2. The model 1 is the basic form of the simple Risk-Lavagna. So here I don't have to explain anything. This is the same as before. Good. So now we go to the main file, because we call the model from R, from the main file. So here beginning, we load quite some libraries. And then here I load the data, and we put everything in the data list, right? Because Stan only takes data list. Well, maybe here I have to do this. Yeah. And then this one is really the same as before. So here we give the path of the model file, and then we say how many samples, how many chains we want to run. And here is running the first model, and here is running the second model. yeah, let it run. So this one, we will calculate the likelihood of the first model, simple risk Wagner, and here we calculate the likelihood of the second model. So when we have the log likelihood matrix, we can easily calculate either the LU or the WAIC. When we have the results, we take the lower or the lowest information criteria, and we take that one, and that model is the best model. And if we also want to do it a little bit more quantitatively, there is also a function called compare to compare these two. But the comparison doesn't really give us too much information. It basically shows the difference, and we can calculate the difference quite easily, right? And we can calculate the difference by using this and minus that, the same. Good. Any questions? Yeah, so compare is the LU package. Compare is the LU package. Nowadays, because there are so many R packages, if you want to make it a little bit more explicit, I recommend doing this way so that you know this function belongs to this package. This function also belongs to this package. This one, rstan, for example. Yeah, same here. Good. And one small tip is that if you write this way with this double colon sign, then you do not even have to load the library. So this is the difference. It's quite interesting. Sometimes at the beginning in Python as well, you have to import a lot of libraries, and all of the first maybe 10 lines in the script, they are dedicated for importing or loading packages, libraries. And sometimes you are repeating yourself. It's a little bit tedious. If you want to avoid doing that, you can do this way in R. I don't know how to do that in Python. Maybe not possible, right? If you want the shortcut like NP, for example, for NumPy. So anyway, in R here, this is possible to avoid loading explicitly, and you can call the function here in this particular case. Good. Any other questions? So the model might run for some time, I don't know. Any questions? So what I can tell you is that we don't even have to wait until the model is finished, because we just run everything. There's no error, and we've seen how the model is coded, what are the differences, and how to use different blocks to specify the variables and also to optimize. And we know that already, and running is really the least interesting part. So supposedly we run that and we've seen the results. So here I have copy pasted the results from the running objects. So what we see here is that first model, remember first model is the simple risk Wagner. The second model, that is the counterfactual, the double updates, okay? So the counterfactual updates. As I said, we look at here the very last line. This one, nearly 800, and then this one is nearly 600. So the difference is 200. And this one is lower. And I said lower is better, take the lower one. So the second model, the double updates, counterfactual risk-Wagner or counterfactual reinforcement learning is the best out of the two, at least. So here, if we want to draw some conclusion, is that, well, we run a simple reversal learning task. We recruited data from, how many people here? Yeah, here we recruited data from 10 participants, and we tested two models for the potential cognitive mechanism One is the error-driven simple Riskler-Wagner model, and the second is the counterfactual double updates reinforcement learning. And using the stand for model estimation and using the loop package, calculating the leave one out cross-validate, not really cross-validation, leave one out information criteria, and we show that the counterfactual double update model is the best. And then you report the results. And this is basically how you do it in reality and how you describe everything in your paper. Great. So there is a last thing, which is called the posterior predictive check. I didn't really spend too much time on the PPC, so this is called PPC, the posterior predictive check, because previously it doesn't really make too much sense to look at it when there is only one model. It makes some sense, but it makes better sense if we have multiple models in this case. So I'm bringing you this idea here. Posterior predictive check, the meaning is that we have the raw data, we have the actual data, the observed data, and we have a model. Why we want to do a model? Why we want to do modeling? It is because we want to approximate the possible potential cognitive process. So why the participants are making this behavior and why the participants are making that behavior, why they choose blue, why they do not choose yellow. So this is the question. We want to make approximation. We want to model that. That's our purpose. And when we model that, then we also want to evaluate how well our model could capture the variance or the pattern of the observed data. Okay? So what we can do? We could ask our model to generate data. This is fake data, right? Because those are generated. So we could ask our model to generate data, and then we could compare if the pattern of the generated data could follow the actual observed data. So if they match, that's very good. And if they do not match, we then have to go back to the model to find where we can improve. So posterior predictive check serves two purposes. One is really to check how well your model could capture the pattern of the data to validate the model. This is one purpose. Let's call it validate. The second purpose is falsify. Falsify means if the posterior predictive check doesn't give you a good results, that means the model generated data doesn't really follow the data, and then you will have to see, well, where is false in this particular model? Where it can be improved. So go back to the model file to improve it. So let me summarize. Two purposes. One is to validate, the other one is to falsify. Okay, very important. The concept you know already, and then let's see how that looks like for our particular case. We have the actual data in this line. So there is the dot. The dot is also actual data. The dot here, here. So they are the probability of choosing the correct option, averaged across participants. The x-axis, the trail. So here is the data. The curve is the data averaged across all those participants. Okay. And as I said, for doing the PPC, we ask our model to generate data, and we could analyze the generated data the same way as we did for the real data. So in blue and in this red pinkish color, you see they kind of follow the pattern of the actual data. So both of them, they are doing a okay job. And there is a slight difference, is that you see here, the uncertainty range of the blue one is larger than the uncertainty range of the red one. So that basically means, even though here by just eyeball checking, they follow both okay, the real data, but the uncertainty of the simple Riskler-Wagner is larger than the counterfactual model. In other words, that means it is less precise, okay? So we could do it a little bit differently. So suppose we analyze the choice accuracy across the participants, also across the trails, and we get only one number, right? So let's say we have 10 participants, and each of them, they do 100 trials. And we calculate how often they choose the best option. And in this case, it is accuracy. And we can do this calculation average across participants and also average across trials. And this calculation only get one result. So in this case, this line is the actual data. And we could analyze the model-generated data the same way as we did for the real data. And because we are doing Bayesian analysis, everything is a posterior, and we could plot the posterior averaged accuracy from each model. So again, the blue one is the simple risk lagna, and then the red one is the double updates. So you see here, the line, the actual data, it's centered around the double update model and not the simple risk lagna. So then that basically means the posterior predictive check is validating or favoring the double update model. Okay. A little bit explanation of the details of the two models. We have the simple risk lagna and then double update risk lagna, however you call that. So we can first look at here. This is a time series of the model from trial number 1 to trial 100. Here the x-axis showing the choice, either A or B. So A is represented by yellow and B is represented by blue. And then the stick here, those sticks, those bars are representing the choice. So here the participants chose blue first and then yellow, blue, blue twice, and yellow twice, blue, blue twice, and yellow, and multiple times of blue, and here really a lot of yellow. So those are the choices, actual choices. On the top, they represent the outcome. Blue means a win, and then red means a loss. Good. And there is a double y-axis. There is a secondary y-axis. Then that is the value calculated from the model. So here the yellow curve, that is the value of choice A, and the blue curve is the value of choice B. Okay. And similarly here, all of the meanings of the curve and the sticks and the colors and bars and the axes, they are the same for the second block. So this one is for the simple single update model. This one is for the double update model. So for educational purpose, I fixed the parameters to be the same so that we can really compare what the difference is between the two models. Quite intuitively, we see that if the option is not chosen by the participants, then the value here is simply not updated from the simple model, from the single model. Only the chosen value is updated by definition. And then here, because we know there is the structure, the counterfactual structure, if one value goes up, the other value goes down. So here we see there is an imperfect anti-correlation. You see here, when the value of the blue goes up, the value of the yellow just goes down, okay? And then this goes back and forth, back and forth. So what we can do now is that we can calculate the value difference between the chosen one and the unchosen one. The value difference means if we say here, I choose blue, the blue value is here, the yellow value is here. I take the difference. This is the value difference. I only I always do V of chosen minus the V of unchosen. So this is the value difference. So I calculate and plot the value difference, both for the single model and also for the double model. And then I plot that here. So showing red, that is the value difference of the simple single model, and then showing blue, that is the double model. Okay. So now you can see what the difference is. So the difference is that on average, the value difference calculated from the double update model is larger than the value difference calculated from the single model. That basically means that the blue one is nearly always on the top. Here, larger than red, blue larger than red, blue larger than red, blue larger than red. Okay, I'm not ignoring here. Here, red is larger than blue, but on average, you see if you calculate the average, the blue one is larger than the red one. Okay, And what that means, how to interpret this. So value is used to calculate action probability using softmax. So if the value difference is larger, then that means the probability of choosing that particular action is also larger. In other words, that means if the value difference is larger, then it is much easier for the participants to decide on the option that has a higher value. So the choice is easier and also more consistent. So that is the difference here in this counterfactual reversal learning task. So when they know there is a reversal structure and if one is good, the other one is bad, they could take the advantage of this knowledge and then to make an easier and faster decision by employing this strategy relative to this strategy. This might not be true, but let's assume there are only this strategy here, and the second one is better than the first. So why I'm saying this might not be true is that the participants, the real people, they might use really something else. But here we simplify that into 2 examples, and then we compare and then we find which is better, which is worse. Good. So nearly the time. Then my part, any questions? And today, if you have the time, do this again, okay? So you can watch the video and so to see how I did it, but actually there's nowhere you have to change. The model is complete, the code is in the R file is also complete. Run that, get a feeling, is in particular, run the last part. So how to extract the likelihood, check the dimension of this likelihood variable, and to see how this LU or WAIC are calculated, and then also how to make inference when you have the information criteria number. So lower is better, the lower the better, that's the take-home message from today. The lower the better, always AIC, BIC, DIC, WAIC, whatever IC, the lower the better. And another take-home message is validating the model is also very important. Model comparison only tells us which is relatively better, which is relatively worse, but how good that is, we don't know. We have to validate it. And the way to validate the model is to do posterior predictive check. We run posterior samples. We generate fake data and compare if the pattern matches the data we observed, the real data. And that's it. Any other questions?